So now that we know what polar curves look like and how to graph polar equations, it's really going to help us with all of our calculus that we have to do with polar equations. So we just need to refer back to that the sheet that has all the different types of polar curves, the limacons and the lemniscates and the rose curves and the circles and all that. And just refer to those when we need to for the patterns and stuff. All right, so we're getting into the calculus part. So how do we take a derivative of a polar curve, and how do we find the slope of tangent lines and vertical and horizontal tangent lines? All right, so our outcome is I can differentiate a polar equation and find the tangent line. So this is target 10-3B. So this is the second part of 10-3. So first of all, this is the slope, woo-woo, of finding how to find the slope of tangents to a polar curve. So this is how you take your derivative. All right, so dy dx, all right, dy dx, because we've got our polar curves written as parametrics here. So we have dy dx equals, and we're going to be taking the derivative in terms of theta. So it's going to be dy d theta divided by dx d theta. So we're going to take the derivative of the y parametric equation. So this is a product because r for polars, r, since that's one of our variables in a polar equation, this is not a coefficient, this is a variable. So we have to do product rule. So we have to do first times the derivative of the second, that's going to be r cosine, plus the second times the derivative of the first. And they do it backwards from what I do. They do the derivative of the first times the second plus the first times the derivative. I can't even do it backwards. The first times the derivative of the second. Okay. And then we're going to do dx d theta. We're going to do the same thing. And this is a product, r times cosine theta, because r is a variable in polar coordinates. So it's going to be derivative times the function plus derivative of cosine times the function. And that's how you get negative sign, because the derivative cosine is negative sign. So this is just the derivative of the y function, derivative of the x. And so this is the derivative of every polar curve. So we just need to memorize that it's dr d theta of sine plus r cosine. And on the bottom is dr d theta. And it's cosine minus r sine. So I just remember the top row, really. I just remember that this is sine theta plus r cosine. And so then on the bottom here, it's the reverse, cosine minus r sine. So that's just the way I always remember it. And I always write it down when I'm working it out. Now, how do you do tangent lines at the pole? So remember, tangent lines at the pole mean at the origin, all right? Tangent lines at the pole. And when you're at the pole, that's when your r is 0. Remember, r is the variable that represents the distance from the pole. So if you are at the pole, which means you're at the vertex, that means the origin, that means your r distance from the origin is 0, right? So that means r is equal to 0, because when you're graphing these polar curves, the r is your distance away from the pole or the origin. So if you're at the pole, your distance r is theta. So that means the function equals theta at that value. All right, at that theta value. So what happens to the derivative when r is 0? So that means this part goes away, this part goes away. That leaves you with this part. All right, so then the dr d thetas are going to cancel. So then you're left with sine over cosine, and sine over cosine is tangent. So if you're wanting to do a tangent line at the pole, then you're only looking for dy d theta equals tangent theta. Okay, so your derivative is just tangent theta. And the only thing is the dr d theta cannot equal 0 in that case, because then you'd have 0 over 0, and that would be undefined. So the dr d theta can't be 0. So if you're looking for tangent lines at the pole, then you just have to look at the derivative equaling tangent theta and go from there. All right, so that's just a special case. All right, so that was short enough that we're just going to keep on going here with the rest of this. All right, so example number 1 says find the derivative of the curve r equals 4 sine theta. Okay. I always write out my derivative. Okay. So my derivative dy dx, that equals dy d theta over dx d theta. All right, and that equals, so here's the actual derivative, dr d theta, and I always just write both of them top and bottom. All right, then the top one is sine theta plus r cosine. So the bottom down here is cosine theta minus r sine theta. So that's the way I memorize it, all right? I just write it in that pattern every single time. All right, so if I'm wanting the derivative of this function over here, then I'm just filling in this derivative. So dy dx is going to equal dr d theta. So that means I need the derivative of this function dr d theta. So the derivative of this is going to be 4 cosine theta, because I'm taking the derivative of r in terms of theta. This is r. So I'm taking the derivative of this function in terms of theta. So 4 cosine theta. So that's going to be down here too, because that's dr d theta on the bottom. So the top gets multiplied by sine theta minus, and then I actually put r in there. R is 4 sine times cosine. And on the bottom here, I've got dr d theta times by cosine minus, put r in there. This is r. That should be a plus. And on the bottom, I'm going to minus r, which is 4 sine. And then multiply by sine. So notice all I'm filling in. If you're looking here, we have to fill in what the dr d theta is, okay, which is the actual derivative of the function r over here. Then you have to fill in what r is, which is the actual function. So you're doing the derivative of the function times sine plus the function times cosine. And then the derivative of the function times cosine minus the function itself times sine. So that's what you're doing every single time. All right, so what is this going to equal? Dy dx equals, well, 4 cosine sine plus 4 sine cosine, that's the same thing. That's going to be 8 cosine sines. And then in the denominator, we're going to have 4 cosine squared minus 4 sine squared. So there's my derivative. Now, to simplify that derivative, I could divide by 2, right? Because everybody has or actually 4. I could divide by 4 because everybody has a factor of 4 in it. So if I wanted to, don't have to, but if I wanted to, I could divide by everybody by 4. So then that would be cosine squared theta minus sine squared theta in the denominator, because those both have a factor of 4 in it, and this has a factor of 4 in it, so that's going to leave a 2. So you could reduce it if you want to, but you don't have to. Nobody is saying you have to. So there's your derivative. Okay, so that's number 1, finding the derivative. Number 2, let's do another derivative. All right, so again, I want to find the derivative of this polar curve. So I'm on example number 2. Find the derivative of this. So again, I'm going to write it out. So dy dx, I'm actually doing dy d theta over dx d theta. And the way you get that is you do dr d theta top and bottom. And then on the top up here, I'm going to do sine plus r cosine. And on the bottom down here, I'm going to do cosine minus r sine. And that's the way I memorize it. All right, so now we're ready to just fill it in and work it out. So dy dx is going to equal, I'm filling in this formula. It's like a formula. So I need dr d theta. I need the derivative of this function r in terms of theta. So the derivative of 3 is gone. The derivative of 3 cosine is going to be negative 3 sine. All right, so that's going to be negative 3 sine. So that has to go in both this position and this position. So let me put that on the bottom as well, negative 3 sine. So I work in this pattern mode when I'm doing this. All right, now the top gets multiplied by sine, And then I add the function itself. So I have to put r, the whole function, 3 plus 3 cosine theta, and then multiply by cosine. Then on the bottom, we multiply by cosine, and then we subtract the function. My function is still 3 plus 3 cosine, and then we times by sine. All right? So there's my derivative. So if I really just wanted to find my derivative, I could quit because I'm done. I mean, I'm finished there. All right? But if we want to multiply it out to simplify it a little bit, here I'm going to get in the numerator, I've got negative 3 sine squared. And then here I'm going to have 3 cosine and 3 cosine squared. Okay, 3 cosine and 3 cosine squared. And then in the bottom, I've got minus 3 sine cosine. And then distributing this across, I'll have a minus 3 sine. And then a minus 3 cosine sine. Okay. Just still simplifying away here. So can't really do anything miraculous in the numerator. So this is just going to be negative 3. If I could, I could divide everybody by 3 if I wanted to. Negative 3 sine squared plus 3 cosine theta plus 3 cosine squared. In the denominator, I can put these sine cosines together and have negative 6 sine cosine minus 3 sines. And then if I wanted to, I could divide everybody through with a 3. So that would make negative sine squared plus cosine squared. I'm taking out a 3, so that'd be negative 2 sine cosine minus sine. So I could reduce everybody by 3, just leaving that with, these would still be negatives, and that would leave that at 2. So that's just reducing it a little bit. But, you know, you don't have to, even on the free response part of the AP exam, you never have to simplify anything. You just get the derivative and you're done. That's the derivative. All right, so that's finding the derivative. So now let's make use of the derivative. All right, so let's make use of our derivatives. So it says find the horizontal tangent lines of the curve. Now I've put a polar coordinate plane there because I like to have the picture. And going back to our patterns, 2 cosine theta we know is a circle centered on the x-axis with a diameter of 2. So I know it has a diameter of 2 and it's a circle sitting here. So I know that's what this looks like. I mean, and that's why it's helpful to have these little patterns. And then sketching out the picture helps you answer the question. It says find the horizontal tangent lines to this curve. Well, I know there's going to be 2 answers because there's a horizontal tangent line at the top, there's a horizontal tangent line at the bottom. So I'm looking for 2 answers. So how do I find those 2 answers? Well, to find horizontal tangent lines, I need the slope of the tangent line. So I need the derivative. So that's the first thing I'm going to do is I want to figure out my derivative. All right, so I'm going to do dy dx equals. So now remember it's dr d theta, top and bottom. All right, and then after dr d theta, it's sine on the top plus r cosine, and on the bottom it's cosine minus r sine. Okay, so I'm going to fill in and find my derivative. Oops. So now the first thing I need to do is I need dr d theta. That means I'm finding the derivative of the function r in terms of thetas. So the derivative of this is going to be 2, but the derivative of cosine is a negative sine. So I'm going to have a negative 2 sine for the dr d thetas in front of the derivative on both top and bottom. So the top is going to be sine plus my r, and my r is 2 cosine times another cosine. And then on the bottom, it's cosine minus my r function, which is 2 cosine, times a sine. All right? So let's see, can we simplify that a little bit? Looks like we can. So dy dx is going to equal, I'm going to have negative 2 sine squared plus 2 cosine squared. And then on the bottom, we have negative 4 sine cosine. All right, so there's our derivative. So negative 2 sine squared plus 2 cosine squared divided by negative 4 sine cosine. Now, I could divide by 2 if I want to, but again, we don't have to. All right, so what are we looking for? We are looking for horizontal tangent lines. So what's it take to be a horizontal tangent line? All right, well, to be a horizontal tangent line, we want our numerator to be 0. So we want, let me change my color. So we want negative 2 sine squared plus 2 cosine squared to equal 0. So we want our numerator to equal 0. But we want our denominator, remember, to not equal 0. So we'll come back to that here in a second. All right, so let's make this equal 0. So in order to solve this equation, I need to have it either all in sines or all in cosines. So what we need to do is we need to make some type of substitution so that I have either all sines or all cosines. So the easiest thing to do is to use the sine squared plus cosine squared equals 1. So in place of sine squared, remember I'll write it here, sine squared plus cosine squared equals 1. So if I'm replacing sine squared is going to be 1 minus cosine, right? So sine squared is going to equal 1 minus cosine squared, because you're going to move the cosine squared over to the other side. So I'm replacing sine squared with 1 minus cosine squared. So then now my equation's only in cosines, and I'm going to be able to figure out the answer. I'm going to be able to solve. All right, so let's take a look here. I've got, let's see, negative 2 plus 2 cosine squared plus 2 cosine squared theta is equal 0. Just still plugging away. So negative 2, this will give me 4 cosine squared thetas. So that means cosine squared theta, I move the 2 over here and then divide by 4, and that equals 1/2. So now when I take the square root, that means cosine theta has to equal the square root of 1/2, which is going to be 1 over radical 2, which is radical 2 over 2. So now we've got this. We know this. Where does the cosine on the unit circle equal radical 2 over 2? So what theta angles on the unit circle does the cosine value equal radical 2 over 2? Okay? So that's going to be pi over 4. And the other one is going to be, oh, I took the square root. That's right. So it's positive and negative. Because I was like, I got 4 answers here. All right. Because we took the square root, you got positive and negative. Because where it equals positive is going to be 7 pi over 4. Come on. 7 pi over 4. So where it equals positive radical 2 over 2, that's going to be in the first and fourth quadrants. And then where it's negative radical 2 over 2, because we took the square root, so we've got positive and negative. Got 2 answers here. So we're looking where cosine is positive radical 2 over 2. That would be in the first and fourth quadrants. And where is the cosine negative radical 2 over 2? So that's going to be 3 pi over 4, which is in the second quadrant. And then 5 pi over 4, which is in the third quadrant. Because remember, in the unit circle, we've got cosine is your x-coordinate. So here's where we got positive radical 2 over 2, radical 2 over 2. In this quadrant here is where you have negative radical 2 over 2, radical 2 over 2. In this quadrant is where they're both negative, right? And then in the fourth quadrant is where you're positive radical 2 over 2 and then negative radical 2 over 2. So this is 1 pi over 4, 3, 5, and 7. So 1, 3, 5, and 7. So For 1 pi over 4 and 7 pi over 4 is where we have positive radical 2 over 2, and at 3 pi over 4 and 5 pi over 4 is where we have the negative radical 2 over 2. All right, so the question is, where do we have these two horizontal tangent lines? All right, so as this is mapping out along this curve, as it maps here, this is actually going to happen from 0 to pi over 2. So going from here to here, I'm thinking of like the hands of a clock, or like taking this axis right here and spinning it on the pole. As this spins up to here, that's already going to map out and go through. As it turns up to here, it's going to map up this first half of the circle. So that means from 0 to pi over 2, that already maps out the first top half of the circle. And then as this swings around from this way, it's going to map the rest of the bottom half, okay, of the circle. So this circle gets mapped out for theta 0 to pi. So it only takes 0 to pi to do this entire circle, okay? So that means my answers are going to be within 0 to pi. So the top horizontal one right here is going to be the pi over 4, and the bottom one down here is the 3 pi over 4. Because if you do 5 pi over 4 and 7 pi over 4, that's going around the circle a second time. So the 5 pi over 4 is going to hit this horizontal tangent line again, and then the 7 pi over 4 is going to hit this horizontal one on the bottom the second time around. All right, so there are only two answers, and so it's the pi over 4 and the 3 pi over 4. All right, so the question asked for, find the horizontal tangent lines of the curve for r equals 2 cosine theta. So it just said find them, so it's just finding where they are. So one of them is going to be at pi over 4, and the other one is going to be at 3 pi over 4. All right, we don't have to find the equations or anything. We just have to find where they are. All right, next one. Now for this one, let's find the vertical tangent lines. All right, let's find the vertical tangent lines. And then I will stop this video, and then I'll start a second one for other examples, so this is not so long. All right, so we'll do this one, find the vertical tangent lines. No, I think what I'll do, let's see, because that's only 4 examples. I think I'll quit right here and pause this video and make a new video so I'm not so long, because I've already done 3 examples. So I'll do the last 3 or so examples on a separate video.